Today we're going to continue on with covalence. For your prep work on Friday, you all received a copy of this image along with some thinking questions. And for the most part, everybody who answered had very, very thoughtful and kind of logical responses, meaning I could see where you were going, especially with those more complicated ones, like how does ionics show what's going on with the electrons? How does covalent show what's going on with the electrons? And overall, you guys did very well, okay? Key things, similarities and differences. Similarities, they both have atomic symbols. They both have dots to represent electrons. Biggest differences is that ionics have ions, okay? And we know we have ions because we have these brackets, we have the charges, and covalents, those are nowhere to be found. But what's new on the covalent are going to be these lovely little lines and stuff, which we're going to learn what they mean today. But a lot of you got basically the right idea in your thinking questions last week. Okay. One quick note, this calcium picture was actually incorrect. It should have brackets as well, like I just drew. But it is what it is. The internet's not always perfect. Neither are we. So we're still learning. Okay. And so the biggest difference is that ionic compounds are showing a transfer of electrons. That's why you have positive charges. That's why you have negative charges. Whereas covalent, what's going on with the electrons is that they are being shared. Okay, and so you can tell that they are being shared because they are drawn in the middle of two atomic symbols. This dot and this X represent two electrons that are being shared between this hydrogen and this oxygen. This line here represents electrons being shared between the carbon and the outside chlorine. Specifically, each line represents two electrons. Okay, the only way that I thought you guys might be able to figure that one out is with this picture up here for nitrogen. These are the same picture, just written in different ways, where they are showing you that nitrogen share 1, 2, 3 pairs of electrons, and so they can be replaced with 3 lines right there. Okay, and so a lot of you guys were on the right track. You were like, I think those are the electrons being shared. I think those are the ones that are forming the bonds, and that's exactly right. The next step is identifying how many electrons are represented by each line, which is always going to be 2. So in this case, how many electrons are being shared between this carbon and this oxygen that I just circled? There are 2 lines, and each line represents 2 electrons. And so most of you did get it. Thank you, Arfa. Calm down. It is, in fact, 4. Okay, this picture could be drawn in a different way where you would have carbon and 4 dots next to the oxygen. This is for those of you that did the collisions game and you went past level 6. It was starting to go into these, what are called double and triple bonds, which we'll talk about in the future. Okay? So what we're going to do today is I'm going to show you how I would draw a Lewis dot diagram for a covalent compound from scratch, but I'm mostly going to be pointing out what you're going to be checking to make sure that what you are doing is correct. Okay, and that is what your asynchronous work is going to be. You're going to be given 6 compounds and then 3 to 4 multiple choice options, and you're going to be tasked at identifying which one of them is correct. Okay, I'm going to reset my screen share right now. In the chat, please tell me how many Lewis dot diagram or valence electrons carbon has and how many hydrogen has. Arafat, while I'm doing that, what is your question?
My question was, what if an odd number of electron was shared? Say
That's not
it
going to
wasn't
happen.
pair.
That's not going to happen. You're going to see why today in this first example, okay?
Okay.
It always is going to end up being a pair of, oh my goodness, I keep clicking the wrong thing. A pair of at least 2, okay?
Okay.
All right. Thank you, Alexander, and thank you, Rosemary. The example we are looking at today is the one we just named in our warm-up, CH4, carbon tetrahydride, otherwise known as methane. Okay, and the first thing you always need to do when drawing a Lewis dot diagram is count your valence electrons. Okay, because valence electrons are the ones that are doing the bonding. They are the ones that are going to be shared or transferred depending on the bond type. Here, 2 nonmetals, they are going to be shared. Okay, and so the easiest way to do this is to just look at your periodic table. Remember, your valence electrons are going to be the last number in your electron configuration. And so for carbon, we have 4 valence electrons, and hydrogen, we have 1. Okay, but we also want to take into account that we have 1 carbon with 4 valence electrons, and then 4 hydrogens, which each have 1 valence electron. Okay, and so the key thing is you are counting the total number of valence electrons for every atom, not just every element, but every atom. Okay, and so you can do this a couple of ways. You can either do it as I have just drawn here and literally draw them out to get 4 plus 1 plus 1 plus 1 plus 1. Or you can do some math. You can take the number of valence electrons from carbon, add it to the number of valence electrons from hydrogen, but also multiply that by however many hydrogen atoms you have. So in this case, 4 plus 1 times 4 is the same as 1 plus 4, which is equal to 8, which if you count all the dots, 1, 2, 3, 4, 5, 6, 7, and 8, 8 is our magic number here. Okay, and so what this is telling us is that our final picture has to have exactly 8 valence electrons. Okay, no more, no less. This has to do with Arfat's question, what if there's ever an odd number that are shared? We are dealing with covalent compounds that are going to end up being neutral, meaning ultimately an even number of electrons will be shared, and that will be the case because of the ratio that has to happen in order for every atom to fulfill the octet rule. You guys may have thought that we were done with the octet rule, but we are not. Okay, in the chat, if you remember, go ahead and type what the octet rule is. You can actually type it to everybody. I just opened the chat. The octet rule is kind of like the guiding force in figuring out what types of chemical bonds and stuff we are working with. It is going to be what determines how the elements are going to work with each other in order to, as Gabriel put in the chat, have a full valence shell. Okay, Sadia is pointing out for most atoms, this means having a total of 8 valence electrons. Okay, the goal of forming chemical compounds, the goal of forming a chemical bond is to achieve a stable electron configuration, which means having a full valence shell. Okay, and so that's what these atoms are doing. That's the only reason they want to form bonds. Okay, and so what we're going to do now is we're going to put the puzzle pieces together. Where if you did the collisions game last week, you have a little bit of a heads up to this, but I'm going to walk through it all step by step and show you how you check this to make sure that these two things are correct, that you've used the exact number of valence electrons, and that everybody has their version of the octet rule fulfilled. Okay, so I'm going to start with carbon. Carbon, spoiler alert, always goes in the middle, and it has its 4 valence electrons, tops and sides. And carbon needs 4 more electrons. And so what's going to happen is carbon's going to come along, be minding its own business, and be like, oh, hey, hydrogen, I have a question. I see that you want an electron. I need some help to get closer to my octet. Can we work together? And that's exactly what this hydrogen and carbon will do. They will work together so that this hydrogen is now happy with 2 valence electrons. In the chat, remind us why hydrogen is happy with 2 valence electrons. And carbon's getting closer. Carbon's not quite there yet, but it has 1 more electron closer to that full valence shell. And so if you notice, carbon tetrahydride has 4 hydrogens. Okay, and so Isaac's reminding us in the chat that hydrogen is happy with just 2 valence electrons because it only uses that first electron shell. Okay, and so I have 2 hydrogens here, and carbon's like, oh, I'm almost there, halfway. And carbon's like, I have an empty spot right here. I wonder if I can find another hydrogen that can fill that in. Hydrogen will be happy. And now I have another empty spot right here. Can another hydrogen come in, fill that in, and be happy? So now we have 4 hydrogens that are happy. Let's count how many total electrons we have drawn. 1, 2, 3, 4, 5, 6, 7, 8. So we've used all of our electrons, and all of the hydrogens are happy in terms of the octet rule. And if you also look at carbon, like a Venn diagram, the electrons in between the letters are being shared between those two elements. So these two are being shared between this carbon and this hydrogen. Same with these two, and these two. And if you notice, carbon now has a full valence electron shell. Okay, so everybody, we've used exactly 8 electrons, and every single atom in this picture has a full valence shell. Now, what I have drawn here is a lot of like show your work examples. It's not perfect. What you're going to do to finalize the picture is you're going to get rid of these circles. I'm going to put the carbon and the 4 hydrogens surrounding it, and I'm going to put my 2 dots like this. This is a completed Lewis structure for carbon tetrahydride. Or what else could we do to simplify this drawing, because chemists are lazy? What else could we do?
For
Almost,
each pair of
Alexander. Go ahead, Arafat.
for each pair of electron, we put one line down,
Exactly.
connecting them.
This pair of electrons we can replace with a line, remembering that one line represents 2 electrons being shared. Everything still works out. We have 2, 4, 6, 8 electrons. Everybody's happy, and that is your completed Lewis dot diagram for carbon tetrahydride. Okay? If you were looking at another example, for example, NH3, this picture you are going to learn is incomplete. If you don't like the lines, you don't have to use them. I also have the dots available to you. But this picture is incomplete for both reasons. Number one, total number of electrons, nitrogen has 5, hydrogen has 1, and there are 3 nitrogens, giving me a total of 8. Right now I have only drawn 2, 4, 6. So we have not followed the valence electron rule. And also, if you look at poor little old nitrogen right here, nitrogen is not happy. It still needs 2 more electrons, which is good because now we have drawn a total of 8 valence electrons, and everybody is happy. Okay, so before I start showing you guys how to draw these Lewis dot diagrams from scratch, which by the way, this is the fastest I've ever had to teach it in my life. So if you are confused, you are rightfully allowed to be confused, because this is a longer topic that's very difficult to teach in 20 minutes. Okay, and so what I would like you to do for your asynchronous work today, Alexander, I see your hand up, don't worry, is on Google Classroom, you were just assigned a prep work assignment. And essentially what it is, where is it? There it is. Nope, where is it? Scheduled for 1:50 p.m. That's right now, by the way. I'd like to let you know. Thank you. That was actually 2 minutes ago, Google. What you are going to see is a Google form, and there are 6 chemical compounds. Okay, Google, we don't have time for this. Let's go. Oh, now my actual Google was listening to me. What you are going to see, if my computer would ever load, is you're going to fill out your name, first name, last name, all that good stuff, section number, and then you have 4 diagrams. For each question, it says which Lewis structure is correct for fluorine, for nitrogen, for oxygen, so on and so forth. The 2 things you are going to check are listed up here at the top, that the exact number of electrons are used, meaning you count your total number of valence electrons, and that each element has a full octet. Okay, I am not expecting 100% accuracy with this. This is just practice for you all to see if you can start to analyze these pictures and decide which ones are more correct than others. You're going to get your score immediately after you do it, so you can look at your work, check your work, and we will go over these more tomorrow. Okay, to be perfectly honest with you, we are not ever going to be drawing any Lewis structures that are this complex. These guys you will see pop up. We will more so be dealing ones like carbon tetrahydride like you just saw, and we'll be going from there. Okay, we're going to start drawing tomorrow. Today, I want you to use what you learned to check how accurate these pictures are. Okay?
Is this for homework?
Yes. If you look on the Google Slides, I have walked through the process for carbon tetrahydride as well. And I have another example for silicon tetrafluoride if you want to use it before you try your prep work assignment. Okay? If you need to go, you can feel free to exit the call. If you want to stay for the next class and watch me go through the whole thing again, you are welcome. But right now, Alexander, what's your question for today?
Oh, sorry, I had a quick question about the lines, but then I just watched the image and then I just
You figured it out?
yeah, I figured it out. Thank you.
Okay, great. Feel free to email me if you guys have any questions, or jump back into the same Zoom call at 2:15 p.m. where I will be walking through some more examples during office hours if anybody needs me to. Okay? Otherwise, I'll see you tomorrow, my friends. Have a great day.
Bye,
Bye.
miss.
Bye.
Bye.
See you tomorrow. Bye.